Okay, now we did try to reduce the computation time, and it really go happens that the computation time cannot be really reduced because these days we talk about a lot of data to really train the neural networks, deep learning, lots of data, and you know that even training them for one iteration requires a prolonged time, and neural network using backpropagation algorithm requires lots of iteration. Now imagine neuroevolution, too many iterations and too many simulation runs and too many individuals, too many generations. Is that feasible? No. The problem over here is let's try to understand what's the limiting factor. The limiting factor is that I've got a small robot with a small processor and it's learning things on its own. So why not just try to, for the training phase, give it a lot of computational hardware, let it run using a lot of computational hardware in order to accelerate the training. The other problem is that when you write down a computer program, the I/O really takes in a long time because it's a separate device, it's a separate stream for which you need to get the data. So that's a slow process. In contrast to the real matrix multiplication, which in GPUs could be now done extremely quickly. And same problem is there with the physical robots. You are loading a controller, you're loading a neural network on a robot, then you're taking readings from sensors, which is slow with the interface as an embedded system that's slow, and then you're running the motors which is also slow. So there's a lot of device IO which can really slow down the system, and therefore if you really want to accelerate learning, our mantra is of course to use simulations instead of real hardware. So with simulations, a lot of things improve. With simulations, a lot of things improve. So first of all, a simulation is a completely a software package. So yes, the UI takes time, but you can always shut the UI off and then it goes extremely fast. You've got the multi-core technologies these days, which makes it more fast. In fact, you've got clusters of computers. So these days, it's not uncommon to say that, yes, I'll deploy 1,000 nodes. So it's like 1,000 machines in parallel. Just imagine that. So your learning becomes 1,000 times more efficient because each system is simulating a robot and noting the effectiveness. So that goes extremely fast. It can be heavily parallelized because it's a software. It can be extremely parallelized because it's software. The slow hardware IO interfaces are not there. So in simulation, a neural evolution happens in exactly the same thing, in exactly the same way. Instead of a physical robot, you've got a simulated robot, and because it's simulation, it's extremely fast. Now, in the real sense, what's the difference between a simulation and hardware? So a simulation could be noiseless, and in hardware you have noise, but then of course most of the simulators these days, they try to model different noises and you can set the noise level, so you can realistically set the noise levels that you might expect in the hardware. In fact, these days people also try to take different components, sensors, actuators, and note down what are the noise models, try to note down what are the communication delays, what are the frequencies of operation, and then try to make simulators which emulate exactly the same noise model from data which is obtained from the real hardware. So you make a realistic noise model and then give it to the simulation. Now it really turns out that it's not a very important thing as well to have as realistic noise models as possible, because what I do is, so that's my neuro evolution for evolutionary robotics. So I generate initial population, I evolve in simulations, So I get extremely competitive ones. Then I evolve in real hardware. So what really happens is this evolution, it makes sure that the population is not random, it's not near random, it's extremely powerful. It's extremely competitive. It's trained on clusters, parallel system with realistic noise models, with realistic actuators, with realistic sensors, with realistic worlds, with realistic wheels. All those things beautifully modeled in the simulators. So people say that the simulation technology has increased so much that these days you can actually have simulators that behave exactly the same like the real robots. So a lot of data is taken from the real robots and that is simulated to get the real noise models. So I make an extremely competitive population pools of recurrent neural network. Then what I do is I just need to do a little fine tuning that the real hardware is behaving differently here, 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 here. So that little tuning is required, and that little tuning is the one that happens with the real robot. So in reality, what the evolution on the real hardware is doing, it is nothing but it is on the real hardware, just fine tuning those models a little bit to account for the differences between the simulation and the real hardware. Now, sometimes what really happens is that you want to do a simulation, but you may not have the robot model. So, what's the simulation around really? So, you've got again your robotic agent, the actuators over here, the sensors over here, and this is the RNN model. And then I've got a simulated environment. And here I have got in a simulated environment. And the simulated environment consists of a lot of things, including a simulated robot, which needs a robot model. So the robot model as in the simulated actuators, the simulated sensors, so that's a robot model. Let's only talk about the actuators. So what's a robot model? It says that if I'm at a state S at time t and I apply the control input at time t, which comes over here from the actuators, what control inputs are you applying? And this is applied for delta t amount of times. So in which state will I be at time t plus delta t? That's a robot model, and that's also called as the kinematics of the robot. So in reality, I take this thing and I add noises over here. I add noises over here. So that's what's called as a kinematics. It's the same thing. V equals to U plus AT, S is equal to UT plus half AT squared. So that's the kinematics of point mass amidst a constant acceleration. So that's a robot, you know that there's a left wheel, there's a right wheel. So all those things will come into account. This one is currently kinematics. You can also deal with the dynamics of it, where you additionally account for the forces and the torques and the mass, which does not come on over here. So that's the kinematics of the robot. Now, luckily for most of the robot, the kinematics are known, but sometimes there are problems. And the problems can be any one of the following. First is, I have the kinematics, but I don't have the parameters that the kinematic equation uses. So the kinematic equation says the length of something. Of course, I can take a measuring tape and measure it up, but the robot body is nice and crooked. Even the wheels are a little bit bent, so I don't know which length to measure. So sometimes I may have the kinematic equation, but I may not have the exact parameters. Sometimes I may have the kinematics equation, but that may be invalidated because of the specific make of the robot. Like the tires are a little drifted, or the robot frequently occurs drift. All these kinematic equations, they assume no drift, and the robot very commonly occurs drift because the rubber quality is not good, the tire quality is not good. One wheel skids a little bit. So the center or the battery is a little bit on the right, because of which the robot is disbalanced and therefore will behave differently. So you've got all these factors because of which you do not know the kinematics. Sometimes you don't know the kinematics at all. So sometimes you may not even know the kinematics at all. So what happens is that in such situations, I really cannot measure, I really cannot simulate. So sometimes you get into this trouble that you want to do evolutionary robotics by simulation, but you cannot simulate it up because your specific robot has peculiarities. It has noises which are not known. It has models which are not operating at their optimal settings, skidding, drifting, everything is there which you assume that's not to be there, or the robot is having parameters which you absolutely don't know. And therefore, what you really need to do is that in the absence of this equation, in the absence of the kinematic equation, in the absence of a dynamic equation, in the absence of any way to find out what is the robot model, this equation F, in the absence of that, you still need to simulate it up, and therefore the technique is called as system identification. So to find the unknown function, kinematic function, where unknown will be unknown by model, I don't know the model of the unknown by parameters, or it can be unknown by wrong assumptions. So for various reasons it's unknown. Sometimes it's known, but I don't know the parameters. If you don't know the parameters, if you get the parameters, there is a lot that you can do, but if you don't have the parameters, there's virtually nothing that you can do about it. So therefore, I'll use a technique of system identification in order to find out what the robot model is, and system identification is nothing but machine learning. So what I do is I operate the robot manually, and as I operate the robot manually, I load the training data. So this is what control input I applied. I'm moving it by a joystick, so I know exactly what to do. The robot keeps a log of it. I know what is the state of time over here. So I know the state of the robot, I know the state of this thing because I use external. Now there's something which is happening only once, so you can use external high precision cameras, motion trackers, 3D lidars, so motion detectors. You can use all external things in order to track precisely the motion of the robot and track its speed and track its trajectories, track the trajectory of every characteristic point, track the trajectory of every moving entity in the robot, so you can get the complete trajectory based on which you fill up this real table. And then of course, once you have this table, all you do is to learn a function which, given this, predicts this. So that's the input and that's the output. Any time sequence, time series estimation does exactly the same thing. The function that comes up is what is the kinematic function or the robot model. So the technique of the identification of the technique of system identification, it just uses a supervised learning. So you teleoperate the robot, you operate it manually, you keep a track of all the system state, the control inputs that you applied, and you just train in the exact same function. So now if I add system identification over here, what will happen is that my step number one will be, given a map, I take the robot, I take it on a tour, manually driven, and I use trackers all around over here. to give me the function, and I learn this to get the system identification thing. So I learned this thing. Now starts my actual thing. Now I only got the system identification thing. Similar thing you can also use for the learning of the noise model of the sensors. Now what you actually do around is that now you have got the complete setup. So this is robot agent, actuators, sensors, and this is your simulated robot. And this of course is the environment. Environment will also have obstacles and everything. So this is the robot model that's used over here. So it takes the actuators as input, it takes this thing as input. The frequency of operation is something that you already know. When you make the table, you actually note down what's the frequency of operation. And this you know it from iteratively. So you know what is this, so you know what is this, and this is what will be fed the next time. So, and you add noise. So that's a simulated environment. So because it's simulated environment, you always know the position at every point of time of the robot. So you simulate this thing up. So this one is what is system identification. And this is evolution in simulations. Make a very good simulator with all the realistic things, with the noise models which are realistic. Run it in parallel in many systems which are possible, and then of course you have the step 3, which is evolution on hardware. And that's exactly the same thing. So you've got the robot agent and you've got the real robot. So replace simulated robot by a real robot, and that is exactly what happens.